In this video, we will show how we can optimize the coupling value between logical components using genetic algorithm. So we see here the functional architecture of the AIDA remotely piloted aircraft system. For more information about this system, you may have a look to the previous article concerning the consistency between the functional architecture and the logical architecture. This is the allocation matrix with the function usages for the rows and the logical subsystems for the column. We will use this matrix to allocate the functions. And this is a simplified initialized logical architecture with 5 subsystems. In this architecture, there is no functions allocated to the logical components for now. So now let's say that we want to find a set of allocation that minimizes the coupling value of the logical architecture. I will first open the options to configure a little bit the genetic algorithm. We can see here several parameters. For now, I will just increase the population size to 1000, since 100 is probably not sufficient to have a good coverage of the solution space. Okay, so I'll launch now the genetic algorithm, and our plugin will transform the functional architecture into an n-square matrix and then call the Python code to return the solution that has an optimized coupling value. So we can see that the genetic algorithm has found a solution in 8.7 seconds with a coupling value of 2.8. Now the plugin refresh the logical architecture diagram. Okay, so all the leaf functions have been allocated to the subsystems. Now let's have a look to the logical architecture. It has been automatically populated with functions and flows between components. Okay, let's discuss a little bit the results. We see that some allocations don't have too much sense. The genetic algorithm does not know the semantics of the subsystems. They could have been named subsystem 1, subsystem 2, or subsystem 3. The genetic algorithm would have provided the same result. For instance, if we look to the control camera orientation, we see that it has been allocated to the propulsion subsystem. The same for record photos and videos and send pictures to database. It would have been better to allocate those functions to the vision subsystem. So to tackle partially this issue, we can fix some of the allocations using our engineering knowledge. Those fixed allocations will not be changed by the genetic algorithm, but they will be used to calculate the coupling value at each iteration. So let's say that we want to allocate the control camera orientation and record photos and videos to the vision subsystem, control UAV attitude and control UAV position to the flight management subsystem. Okay. Manage mission modes and retrieve a point of interest to the mission management subsystem. We will allocate generate thrust to the propulsion subsystem and monitor UAV control to the UAV control station subsystem. Okay. So we have now 8 fixed allocation. So let's see how the genetic algorithm is able to handle those constraints while providing a solution that can be good in terms of coupling matrix. So the genetic algorithm is ongoing. It takes several seconds. Okay, it finds the solution in 11 seconds. With a coupling value of 3. We see now that the allocation has more sense. Check wind force and emergency landing has been allocated to the mission management. sense and avoid obstacles have been allocated to the flight management subsystem. Identify absolute aircraft coordinates to the mission management. Identify defects to the vision subsystem. And you can see that all the functions inside make and record videos have been allocated to the vision subsystem since they are tightly coupled. So this architecture has more sense in terms of allocation, and it has an optimized coupling value. So to sum up, we have shown how genetic algorithm can assist system engineers during the allocation activity. For this kind of problem, it is known that genetic algorithms alone does not ensure the final result is the global optimum, since finding the real minimized architecture is strongly dependent of the number of functions, the number of flows, and the number of possible components where the functions can be allocated. This is a path that needs to be explored in more depth. We have seen also that the genetic algorithm does not know the semantics of the name of the components. Hence, we need to reduce the solution space by fixing allocations in order to obtain an allocation matrix that has more sense. Finally, the algorithm considers only coupling value, but it will be possible to explore multi-criteria optimization by adding non-functional requirements to the fitness functions, such as end-to-end timing constraints. Thanks for watching.